For topic two, we're going to look at solving equations using substitutions. So that means solving trig equations using substitutions. And what I want to remind you of really, really quickly is when we were in the previous video, when we were looking at just the introduction to solving trig equations, there was something that was happening. Okay. For the first equation that we looked at, we had just sine of plain old theta equals a half. And then we looked at 2 times cosine of just plain old theta minus root 3 equals 0. Then we looked at 4 sine squared of plain old theta equaled 1 and 3 root 2 of cosine of just plain old theta plus 2 equal negative 1. So with all of these equations, we were looking at these trig functions where the argument was just plain old theta, which was nice because once we isolated the trig function, we could just go to our unit circle and be like, okay, well, what values of theta give us this particular ratio? But when we get down here, we're no longer going to have an argument of just theta. Okay, so if we don't have an argument of just theta, we can't just go to the unit circle and say, okay, what angles give us this particular ratio because our argument is no longer just plain theta. Okay, so now theta is going to be multiplied or divided by something, potentially added to or subtracted to, or something added to or subtracted from. But for us, we're just going to look at multiplying and dividing. Okay. So, what does this mean? Let's go back to this idea of what we were doing when we were graphing these trig functions, okay? So we had things like y equals a cosine of omega x and y equals a times sine of omega x. That was kind of like our first really generic situation where we were graphing transformations of these trig functions. And what we learned was omega, the coefficient of x, so that thing that our argument was being multiplied by, it really altered the period of our graph. Okay, so omega altered the period of the trig functions. And essentially what we found was that if omega was greater than 1, okay, we would have a situation where our period was actually compressed. Okay, so what it did was it shortened the period, which meant whatever the trig function was, it had to complete a full cycle quicker in like less distance than ordinary. Okay, so like if you think of cosine, okay, cosine has a period ordinarily of 2 pi, so that means from 0 to 2 pi, one full cycle of cosine needs to be completed. Well, if we shrink our period to pi over 2, then cosine has way less time to complete a full cycle, okay? So that means from 0 to 2 pi, multiple cycles would be completed, okay? We also found that if omega was less than 1, what it did was it stretched the period. It lengthened the period, okay? So if our period for, say, sine was ordinarily 2 pi and omega was less than 1, that would stretch our period to where the period would be more than 2 pi, which means sine had more time to complete a full cycle. So it kind of slowed sine down. So that means from 0 to 2 pi, sine may not complete a full cycle. It may only complete part of a cycle. Okay? So this omega was like a really, really powerful thing. It either compressed our period or stretched our period, which sort of sped up or slowed down our cycles of these trig functions. Okay? So in our first example, we have solve each equation, finding all of the solutions for theta from 0 to 2 pi. Okay, well, what is going on and how do we do this? Okay, so let's look at part A first. So we have cosine of 2 theta equals negative 1/2. Well, cosine of 2 theta, that 2 on the 2 theta means something. So this 2 compresses the period. Basically, it shortens it. Okay, which means from 0 to 2 pi, cosine will cycle 2 full times. Okay, and what does that mean in terms of our solutions? Well, if we're looking at the unit circle, we can go and see that just looking at the unit circle with just a plain old theta, we're going to find cosine equals negative 1/2 for 2 different values of theta. Well, if from 0 to 2 pi, cosine is going to cycle more than once, that means I'm going to get more than 2 solutions. So essentially, this is going to double the solutions. So we're going to get double the number of angles that are going to have that same ratio in a certain time period, okay? Or in a certain distance, we'll say. let's look at Desmos. I think Desmos really helps us bring this to life, okay? So in Desmos, let's just graph cosine of theta. So in Desmos, you would just graph cosine of x, okay? So cosine x, and then what we want to do is we want to tweak the x-axis. We know that x represents our angles theta, and then the y-axis represents our ratios. So let's look at this from just 0 to 2 pi. And let's increment by pi over 4 is usually nice. And then from the y-axis, let's just do -2 to 2. That way we can see a full cycle pretty nicely. Okay, so this is a typical, just normal cycle of cosine. Okay, from 0 to 2 pi, this is what we get. Okay, now if we want to know where cosine has a ratio of -1/2, we would graph y equals -1/2 and see where cosine intersects that. And cosine intersects at 2 pi over 3 and 4 pi over 3. So let's go to the unit circle. So I already have it circled. So if we look at the unit circle, remember on the unit circle, these ordered pairs are always going to be of the form cosine comma sine, meaning the x coordinate corresponds to cosine and the y coordinate always corresponds to sine. Okay. And you can see that at 2 pi over 3 radians, we have cosine has a ratio of -1/2. And then at 4 pi over 3 radians, we can see on the unit circle, cosine has a ratio of -1/2. And that's exactly what this graph says. Okay. So we can see at 2 pi over 3 and 4 pi over 3, we're intersecting the line y equals -1/2, okay? So now let's look at what happens if we graph cosine of 2 theta, or in Desmos, cosine of 2x, okay? There we go, cosine 2x. Well, now you can see really clearly that cosine has 2 full cycles from 0 to 2 pi. So this 2 right here compresses the period of cosine, allowing it to complete 2 full cycles from 0 to 2 pi. You can see from 0 to pi, which is like from here to here, we have 1 full cycle of cosine, and then from pi to 2 pi, we have a second full cycle of cosine, okay? So we have double the cycles of cosine from 0 to 2 pi. So now let's look at what happens when we graph y equals -1/2. Well, hopefully you can see that we have double the solutions. So we can say, okay, when x is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, then cosine of 2 times x is going to give us the ratio of cosine equaling -1/2. So we get double the solutions, okay? So hopefully that kind of makes sense. When we have just regular cosine from 0 to 2 pi, we're going to get 2 solutions. But when we have cosine of 2 theta, we get 4 solutions. So by shortening the period, we increase the number of cycles, which increases the solutions. It basically doubles the solutions if you're looking at 2 times theta. So let's go to the worksheet and see what this means algebraically. So when we have a trig function of just theta, we can just jump to the unit circle and be like, okay, well, what angles of theta give us this ratio? But if theta is not by itself, we have to look for a workaround. So what we do is we do a U substitution. So you should be sort of familiar with U substitutions because you for sure did this in 171. So what we're going to say is we're going to let U equal the argument to theta. Now, we know that theta has restrictions. Theta has to be from 0 to 2 pi, but there are no constraints. There are no constraints on U. So we can kind of let U do whatever it needs to do, okay? So here's what I do. I rewrite the function or the equation. Instead of 2 theta, I use just U. So I have cosine of U equals -1/2. Okay, and then I treat U like I would theta. So I go to my unit circle and I say, okay, for what values of U or theta do I have a cosine ratio of -1/2? Well, remember, we get cosine is -1/2 for the angle 2 pi over 3 radians and 4 pi over 3 radians. So we can say at this point that U has to be 2 pi over 3 and 4 pi over 3. Well, that's great, okay? But remember, we really need double the solutions, okay? So here's what we do. We take these values right here and we add 2 pi to each of them. That's going to give us basically 4 values for U. Now remember, U is not the actual angle theta, it's just sort of what we're using for now, okay? So we want to go ahead and find an additional coterminal angle for each of these by adding 2 pi to both of them. That will double our solutions. It'll double the values we have for u. And then when we plug that back in and set it equal to 2 theta, then we solve and get something that works on this interval 0 to 2 pi. So 2 pi over 3 plus 2 pi. Well, I need to find a way to rewrite 2 pi where I have a denominator of 3. So essentially, if I think of this as 2 pi over 1, I just multiply top and bottom by 3. So that tells me if I have 2 pi over 3 plus 2 pi, that's the same as adding 6 pi over 3, which gives me 8 pi over 3. And then I want to do exactly the same thing, but with 4 pi over 3. So if I have 4 pi over 3 and I add 2 pi, that is the same as taking 4 pi over 3 and adding 6 pi over 3, which gives me 10 pi over 3. So I've got 1, 2, those are like the 2 regular solutions. Then I've got 3, 4, okay? Now that's for u. Remember, u doesn't have the constraints of having to be from 0 to 2 pi. And you can see these are right here are definitely bigger than 2 pi. But that's okay, because it's not our official solutions. So here's what we do. We now have to do that whole back substitution thing. Hopefully you can remember from 171, when you do a u substitution, you basically solve the equation for whatever u is, and then you take those values and you go back and you do some back sub. So we know that right off the bat, we said, okay, u is equal to 2 theta. So we're going to set all of these values for u equal to 2 theta, okay? So I get 2 theta equals 2 pi over 3. I get 2 theta equals 4 pi over 3. 2 theta equals 8 pi over 3. And finally, 2 theta equals 10 pi over 3. Okay, now I need to solve each of these for theta. So in order to solve for theta, we solve by dividing by 2. But remember, in the world of fractions, division by 2 becomes multiplication of 1/2. Okay, they're the same thing. So when I divide each of these sides by 2, I'm going to get theta. And then 2 pi over 3 divided by 2 is 2 pi over 3 times 1/2. 2 divided by 2 is 1, leaving me with pi over 3. And then when I take 2 theta equals 4 pi over 3 and divide both sides by 2, I get theta. And then I get 4 pi over 3 divided by 2 is really 4 pi over 3 times 1/2. Well, 2 goes into 4 twice, leaving me with 2 pi over 3. And then if I take 2 theta equals 8 pi over 3 and divide both sides by 2, I get theta. And then 8 pi over 3 divided by 2 is really 8 pi over 3 times 1/2. This 2 goes into this 8 4 times. And I get theta equals 4 pi over 3. And then when I take the last one and divide both sides by 2, I get theta equals 10 pi over 3 divided by 2 is really 10 pi over 3 times 1/2. 2 goes into 10 5 times, and I get 5 pi over 3. So finally, these are my 4 values for theta. And we need to make sure theta is somewhere between 0 and 2 pi. And all of these have a value of less than 2 pi. And you can tell because 5 divided by 3 is less than 2, so less than 2 times pi. 4 divided by 3 is less than 2, 2 divided by 3 is less than 2, and 1 divided by 3 is less than 2. So let's just take a quick minute and jump back over to Desmos. Now remember, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 are our solutions. Let's see what Desmos told us. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So when I take those values for theta and plug them into cosine of 2 theta, I get the ratios of -1/2. Okay, so there you have it. That is solving these equations where your argument is not alone. Okay, so we looked at a situation where our period was compressed, meaning our trig function had to cycle more frequently. So we got more solutions than just the 2 that we would expect. For part B, let's look at the opposite of that. Okay, now I told you up here that when omega was greater than 1, so the coefficient of x, when it's greater than 1, it compresses your period, which means your function has to cycle more frequently, which means you get more solutions. When your coefficient of x is less than 1, it actually stretches your period, okay? So it makes your period longer, which means your trig function cycles less frequently, okay? So keep that in mind. So when we talk about tangent of theta divided by 2, the well, let me write it like this so you know what I'm talking about when I say the 1/2. So I could rewrite that as tangent of 1/2 theta. Well, the 1/2 stretches the period, making it longer, meaning the trig function cycles less often. Okay, so we're going to get fewer solutions. Okay, which means fewer solutions. Okay, now that we know from 0 to 2 pi, we're going to get two values of theta for each ratio that we're looking for. Okay, so let's talk about tangent really quick. So let's go back to, so we're looking at tangent of theta over 2 equals root 3. Let's go back to Desmos. I'm going to have to clear out the old junk. So if you want to clear it out and just go back to scratch, you can go to this like refresh button and it'll let you reload. Okay, so if we're just looking at just plain old tangent, so tangent of x, and let's look again from 0 to 2 pi because 0 to 2 pi represents our unit circle. So we're going to go from 0 to 2 pi, and let's increment by pi over 4. Remember, you just go to the little wrench and you can change your x and your y-axis, and we're going to leave our, we don't care what our y-axis looks like, okay? So we can see that from 0 to 2 pi, it's kind of disjoint, but we do technically kind of get two cycles of tangent. We get one full cycle of tangent, then we get these weird like partial cycles of tangent. But essentially, if I want to see when tangent is equal to root 3 over 2, I can just graph y equals square root 3. And then we can see that we are going to get two values for tangent. We're going to get 1/2, or not 1/2, good Lord, pi over 3 and 4 pi over 3. Now, this 1.7 blah, 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 that is root 3 if you were to evaluate it on a calculator. So we're saying at pi over 3 and 4 pi over 3, we are going to get values equal to root 3. So let's go to our unit circle and just kind of verify. Now, the unit circle is never as easy when you're dealing with tangent, okay? So please keep that in mind. Remember, tangent is the, it's one, we have a quotient identity for tangent, and tangent is equal to sine over cosine. So remember, tangent equals sine divided by cosine. So we need to figure out which ratios of sine divided by cosine, which is really y over x, give us the root 3. And it's going to be these, where sine is root 3 over 2. So if sine is root 3 over 2, and I were to divide it by 1/2, so that's the y divided by the x. I get root 3 over 2 times 2 over 1, which is root 3. Okay, so it's when cosine is root 3 over 2. Okay, so we want to know when tangent equals positive root 3 over 2. That's going to occur at pi over 3 radians. And then down here, when cosine is negative 1/2 and sine is negative root 3 over 2, the ratio of that's going to become positive root 3 again. So at 4 pi over 3. Okay, and if we go back to Desmos really quick, we can now verify that on Desmos and on our unit circle, we get a tangent ratio of root 3 at pi over 3 radians and 4 pi over 3 radians. Now let's talk about what that mean, what it's going to mean if I were to graph tangent of x divided by 2. Well, this is kind of weird. So let's get rid of, whoops, do that. Okay, so we only see two parts to tangent now. We have like these two partial regions for tangent from 0 to 2 pi. So we don't have two cycles anymore. We have like kind of like one cycle. Okay, so I'm going to get rid of that one. So this is now tangent of x over 2. Okay, so if I were to look at when this intersects the line y equals square root of 3, well, now I'm only going to get one solution. So I get half as many solutions as I would have before. Okay, so let's go to the worksheet and see what this means kind of for us algebraically. Okay, there's my worksheet. Okay, so we're going to do the u sub just like we did in part A. So we're going to let u equal theta divided by 2. Okay, so that's going to give me tangent of u equals root 3. And we already know that u is going to be pi over 3. And honest to goodness, I already forgot what the other one was. So, is it 4 pi over? Yeah, 4 pi over 3. Okay, so at pi over 3 and 4 pi over 3, we have those ratios of root 3. Okay, so 4 pi over 3. Now, I don't need to add cycles, okay? So like in part A, we had to add cycles. We had to add like a full cycle of solutions because we knew that we had shortened our period, which is going to double the amount of cycles from 0 to 2 pi. I don't need to do that here, okay? I don't even need as many solutions as I currently have. I need half as many solutions as I currently have. But let's go ahead and finish this process. I don't need to add cycles because I'm multiplying theta by something less than 1. So what I'm going to do now is I'm going to acknowledge the fact that u was equal to theta over 2. So I'm going to take all of these u values and set them equal to theta over 2. And then I want to solve for theta. So to solve, multiply by 2. Okay? So when I multiply by 2, I'm technically doing it on both sides. All right. The 2's here cancel, so I get my theta. And then I get, instead of pi over 3, I get pi over 3 times 2, which is 2 pi over 3. And then on when I have 0 over, or when I have theta divided by 2 equals 4 pi over 3, when I multiply both sides by 2, I get theta by itself. And then 4 pi over 3 times 2 is 8 pi over 3. Now remember, our values for theta have to be between 0 and 2 pi. So at this point, we know we have more solutions than we need because we basically split our period in half, which means we're going to get half as many solutions. Or we didn't split our period in half, we doubled our period, which means we're going to get half as many solutions, okay? So we sort of slowed our tangent function down. It's going to cycle half as many times as it ordinarily would, okay? So I know that 2 pi over 3 is less than 2 pi, but is 8 pi over 3 less than 2 pi? And the answer here is this is bigger than 2 pi. So it's kind of outside of that domain that we set here. So we just want to kind of toss that one, and we're going to say that theta equals 2 pi over 3. Okay? And if we go back to Desmos really quick, we can see that when we took theta and divided it by 2, it lengthened our period, which meant that tangent is going to cycle half as frequently as it used to, which means we're only going to get one solution. So if we plug in 2 pi over 3 in here for x, that's when we're going to get the solution that we desire. Okay, so we get that one solution, 2 pi over 3. Okay, so be really careful with these graphs. This is one way to do this. This is the way that I learned how to do it that just really worked for me. There is kind of another way you do it that I can show you in class if this is confusing. Okay, in the next video, we're going to look at special types of equations where you still kind of do like a u substitution, but sort of in a different fashion.